See, I am a student in solid state electronics material in IIT Roorkee. So here I am going to present how to solve a second order differential equations in MATLAB by taking an example of 1D well. Okay, so let's start. In this presentation, what we are going to cover is first what is the second order differential equations, what is 1D well, and the most importantly, why do we need coding? And then after that, we will move to the coding part, like how we'll code in MATLAB to solve this second order differential equation. And then we will be visualizing the output, like how does the wave function look like for different quantum states. Uh, and its probability density, etc. So let's see what's the second order differential equation. Let's first, before that, let's see what is ordinary differential equation. In ordinary differential equations which contain derivative of one or more dependent variable with respect to one independent variables. For example, dy by dx plus x is equal to 60 is an example of an ordinary differential equations. So the second order differential equation will be containing a second order derivative of one or more dependent variable with respect to one independent variable. Like for example, here the general expression for the second order differential equation is shown like d2y by dx square plus px dy by dx plus qxy is equal to fx, where px, qy and fx sometimes may be constant, and fx may be 0 also. If fx is 0, well, then we will call that equation homogeneous. So let's move to the next part, which is 1D well. What is 1D well? So a 1D well is a model, a quantum mechanical model to study a behavior of a particle, and the in 1D well the width will be very small, because if it is large, so the quantum mechanical effect will not be effective. So for that, width should be around 1 angstrom, and then potential in multiple potential is zero throughout the well, and outside the well it is infinite, so that the particle will be trapped inside that well. This diagram shows how does this look like. Here we can see that Vx is 0 from 0 to L, and beyond that it is infinite. Like at x is equal to 0 and at x is equal to L, it suddenly drop from infinite to 0. And we will give some finite energy to the particle, and then we will see how does its behavior, is the probability of finding the particle inside this well, etc. And we'll be seeing for a particle like electron in the next part. So why do we need coding? The first most important thing is complexity. That is, in practical systems are very complicated. They might have very large perturbations, and uh, it may not be as simple as a 1D well, which is 0 throughout the well, potential is 0 throughout the well from 0 to well. But in reality, there many perturbations. Like here, we can see that potential is minima, then it is increased, then decreased, similar to that. So in that case, manual calculation will not be possible, so we will need help of coding. And second thing is quantum state, to explore different energy states. We know that in quantum mechanics energies are not continuous, they are discrete. So to study different energy states, we will be needing help of coding, because we cannot do practically calculate for the various states. Like we can go up to 10, but beyond that it won't be possible. So third is efficiency, like calculating wave function and probability will be very time consuming, so efficiency also required to be good. So And after that, visualization. With the help of coding, we can actually visualize what does the wave function look like, and what is the probability distribution where probability is maximum and where is the minimum. We can see actually with this with the help of coding, and which won't be possible manually. And other things are comparative analysis. Like we can compare the different quantum states by changing their parameters, like changing width, how does this affect the wave function, how does the probability density changes by changing the different parameters. And which next is scalability. For a more complex system, the variation will be more, like the potential will become more complex also, and it won't be easy to handle manually. So for that, again, we will be needing help help of coding. The next thing is Schrodinger equation. Schrodinger equation is a fundamental equations which describe any quantum state, any quantum of a physical system. So the general expression is shown here, where we can see that del square operates on psi, and here we x psi and e psi, where capital E is the energy of the particles. In our cases, so since we are limited to one dimension, which is 1D well, so we will replace this del square operator with the one dimensional derivative, which is del 2 by del x square, and Vx is obviously 0 from. So we will substitute this value into this Schrodinger equation, and then we will get a second order differential equations. Here h cross is reduced to Planck constant, which is a constant, and let's see how we can do this. How we can solve this. Okay, we will be the most informative things we can collect is probability density. uh, so probability density tells the likelihood of finding a particle inside the well. For example, in this curve, we can see that here it is maximum at x is equal to 0. So in that way, we can see that the particle is most likely to be here at x is equal to 0, because here probability is maximum, and before that and after that is minimum. General formula is shown here. Uh, we can remove we can substitute this limit according to our system, like in our 1D well, our wave function will be just lying from 0 to L, so we can change this limit in our calculations. MATLAB, in a MATLAB doesn't it does not have facility to solve a second order differential equation. So what we will do is we will change the second order differential equation into first order differential equation by changing some parameter. Like here we have taken psi is equal to psi 1, and this will give me d psi 1 by dx, which I have assumed that equal to psi 2. So we will substitute this value in the in the second order differential equation, this one, we will get then these two differential equations, which are first order. Okay. Before let's see what we will be going to do in the coding in MATLAB. So first we will write a function file where we will define our differential equations and different constant like mass, length, and the value of h cross. Here I have defined m, which is the mass. I have taken the particle as a mass. I'm sorry, particle of a mass in particle as electron. M is I have taken m in the unit of energy. We know that uh, mass of electron is 511,000 electron volt by c square, and h also h cross in the unit of hc, and then L is 1, which is represent 1 angstrom, and then we will define energy E, um, which is pi h bar is equal to 2 ml square. We will we will define these two differential equations. As if we previously obtained these two differential, this psi1 by dx is equal to psi2. So we will define this in these functions, in this function file. Okay, so note that our solution will be containing like since we have two d psi1 by dx, d psi2 by dx, so our solution psi will be containing one column and two rows for that, and we will see in this script file. After that, in the script file, we will be first to give the initial condition, like because to solve a second order differential equation, so initial conditions are required to complete, to finally solve the to get the final solutions. And then I will define x-axis, etc. And after that, I have used ODE45. This ODE45 function is a MATLAB inbuilt function which will solve our differential equations, and by calling the our previous this function file. By I will call this function file and then solve the differential equations. After that, we will our obtained result will not be normalized, so we will normalize that to get correct wave function. And after that, we will plot that normalized wave function, and then we will calculate probability density also to see where is the probability is maximum, where is the minimum, and other things. Okay, so I will now I will go to the my MATLAB and show you how it changes. Okay, here is my function file, which I have called is a wave function. The name of this function file is wave function. Okay, first I have given all the values of constant like m and le, etc. And here is I have defined this line. This idx represent our first order differential equation, and then second line shows the second first order differential equations. And here I have defined d psi by dx as a uh, two row and one column, 2 by 1 vector. After that, let's move to the script part, where first this is the initial condition I have stored in the size0 variable. After that, for x-axis I have used a linspace function. I use a linspace function. What does a linspace function do is it divides 0 to 1 into 100 equal part. Okay, then after that I have used OD45, where I have called this function, which is a wave function, and then second argument is x span like x-axis, and then this third argument is my condition, that is initial condition, to calculate the value of constants. And I stored that output in z and psi. So I will, after that, here I extracted the information like psi. Note that our psi was initially psi1 here. See, psi is equal to psi1. So our final psi is actually will be psi1. Okay. So I have extracted psi1 from this psi, which was in the first column, and then psi2 from the second column. Okay. After that, I have plotted this psi1 without normalizing. After that, I have calculated this normalized psi, because by dividing normalizing constant, and then plotted the normalized wave function, which is the correct form of wave function. Okay. And then in this next part of the code, I have calculated the probability density, which is nothing but the mod of psi square, and then again plotted the value using the plot function, and given other and added other things. Let me just go and run this code and see what does it do. Okay. Okay, so this is the normalized wave function plot. We can see that this is um, here we can see that its value is 0 at the boundary at x is equal to 0 and at x is equal to l, which is 1 actually. So which is the correct, because the wave function should vanish at the boundary, because at the boundary it should be continuous and differentiable, we know that already. So note that this is for the second exercise, because here we see that I have kept n is equal to 3. If I put n is equal to 1, that is for the ground state, then what is the, okay. So again we see we got a plot for the one ground state 1D well, which is actually correct, or because this is a correct form, because for a ground state 1D well the wave functions is half wave wavelength. Okay. This is the probability. See, we can see that probability is maximum in the middle of the well. Okay, so now let's check for the first strategy, that is n is equal to 2. So I will keep just to substitute here 2 and then run the code again. So okay, so this is a complete one wavelength, which is it is a kind of sine wave. Okay, a complete one wave length we are getting, and again we see that function is vanishing at to the boundary. Okay, so in this case we can see that probability is maximum at the 2 point inside the well, and in the middle it is 0. So all these things we can see using MATLAB. And if we go to the 3D, I mean, this is just for 1D, then if we go 3D, we can visualize these things as well. Just changing, and we can actually compare by changing energy and width of the well. And we can also check for other particle. Here I had taken a particle as an electron, so we can see for other particles as well. So let's move to the slides and see the result. Okay, so here we can see what this function does. It actually store the value of constant, and the second part is about differential equation. And the script for we have given the initial conditions and extracted the output in the form of sine. So here is the output. You can see that this is for first statistic. Okay, and this is the probability density for first decided one layer. Thank you.